So what is a variable speed drive and why do we need them? How does this technology all come together? And if we go back to sort of basic sort of motor theory and look at, and then we take the induction motor as an example where we have the stator. And typically within that stator, when we induce some form of electricity, we induce a rotating magnetic field, which is effectively rotating. Now, to get that basically with a motor, we're converting electricity or electrical energy into mechanical energy. So we're converting electricity to some form of movement, which is in the form of the rotor here. So when we generate, some form of electricity into the motor, it's then inducing that magnetic field, which is in turn causing that rotor to turn. So we have on the motor itself a magnetic field speed, or a synchronous speed, and a rotor relative speed. And because of the losses that that are taken into factor with motors, such as the iron and core losses, we have a thing we typically have a thing called slip, where although the magnetic field speeds are running at one speed, we're not going to get the exact same speed on the rotor itself. So we're going to have some form of slip on there at least. If we go into a bit more detail on the motor itself, you can see there that as a typical overview of an induction motor is that the stator windings, as we said, generate in north and south because of the way they are wound. And typically the poles are paired in opposition to basically generate that electric field to then get that rotor to basically rotate, really. And the rotor bars themselves are arranged as a squirrel cage, where another common term for induction motor is a squirrel cage motor or squirrel cage rotor motor. So in terms of how this all goes together, basically speed is governed by the above equation there, where our synchronous speed is equal to our supply frequency, which is F times by 60, and we divide that by the number of poles over 2. Apologies about that. I think there was a slight sound issue, but going back to the equation, so as we said, speed's governed by what we class as the synchronous speed, which is equal to our supply frequency times 60, and that's all divided by the number of pairs of poles, so the number of poles divided by 2. So for example, if we typically take let's say a typical 4-pole motor, you can see in the equation there that we've got a supply frequency of 50 because it typically would be connected into the UK, times by the 60, and then we divide that by 4 over 2. So it's the 4 poles divided by 2, and that gives us a synchronous speed of about 1,500 RPM. And typically, obviously in an ideal world, you'd like to have that speed, but because of the losses that are involved with those motors, you're going to have that slip. So typically that slip can be anywhere between sort of 2 to 5 or 6%, depending on the motor that you're using. But on average, if we assume less the 3% slip, you're going to get something in the region of about 1,455 RPM. So as we were saying before, you're not going to get in an ideal world, you'd like that exact speed of 1,500 RPM, but in reality, because of the slip, you're going to get something closer to, in this example, 1,455 RPM. Now, if we were to connect that motor, onto the mains supply per se, we're only going to have one supply frequency on there, 50 hertz, and as a result of that motor would only ever run in what can only ever operate at one speed, and that would be at the motor's nominal speed or full speed at least, because we have no means there to control that. So there are other ways or various motor control concepts that we can to achieve this speed control if we wanted to reduce reduce or increase the speed. And there's typically three ways of doing that. The first one is obviously changing the number of pole pairs. So obviously we've got 2 pole, 4 pole, 6 pole, 8 pole, all the way up to sort of 10 or 12 pole, more sort of 8 pole typically on an induction motor at least, where by changing the number of poles on there we can actually reduce the speed. So the more poles on there, the less speed there's going to be. But to try and do that physically is it's not an ideal solution. The second way of doing it would be to change the slip, but to alter the slip somehow, so that the larger the slip, the slower it will be. But again, the problem behind that is when you're changing the slip, you're going to seriously reduce the overall efficiency of that motor and apply much more power into there than what you're actually getting out of there. And the third and final way, and this is predominantly done by all sort of VSD technology, is to effectively change the applied frequency. So we take that 50 hertz that comes in, and on some of the sort of later slides when we see, we'll sort of manipulate that frequency so that we get something that we can control and vary. Now as a result of that, it will vary the overall speed of the motor. So this is the method that's adopted for variable speed drives, and it's to change the applied frequency, or what's commonly known as frequency control. But on the flip side of that, whenever we're doing, whenever we're changing, altering the frequency that's been going to the motor, the voltage must also be controlled to prevent the motor from basically oversaturating really. So the common term for that is basically V2F control, or scalar, which is also it's come across as well. So how do we actually get this sort of very static, stable supply of say 400 volts, 50 hertz, and how do we get it so that we get to a point where we can actually vary that voltage and frequency to give us that that defined speed that we need to operate the load or motor at, and that's all done within within the drive itself, and it's done via 3 stages. So the first stage is basically is rectification. So the majority of drives, or majority of what they class as 6-pulse drives, have a set of 6 diodes in there, and what those diodes do effectively is they start to convert that AC voltage to a DC voltage, because to try and vary an AC voltage and frequency is not it's very complex when we want to change the speed on a motor itself. So what we try to do, or what the drive tries to do, should say, is we convert it to a DC voltage, or very close to it, and then we convert it effectively more or less back to an AC voltage with a varying voltage and frequency that we have control of. So you can see that the first stage is that we're rectifying that AC signal to represent a DC signal ideally. So on the input, you've got a sort of typical sine wave signal, and then on the output of that rectification, you've got like a half wave rectification on there. So it's still classed as an AC signal, because we need to sort of smooth that out to get to a point where it becomes a more constant DC voltage on there basically. You can see on the right hand side there's a couple of sort of circuit diagrams of what a typical sort of diode rectifier would look like on a drive itself. But obviously, to smooth that sort of AC signal to get to represent more of a DC signal, we need to have some form of what we call a DC link in there, and that can consist of capacitors or inductors with some form of resistance in there, at least anyway. And whether you have capacitors or inductors in there depends on the type of drive that you have in there as well. So a lot of drives in today's sort of market will be what we class as voltage source inverters. So typically we'd have some form of capacitance in there to create this smooth DC link. Very rarely nowadays, there are some current source inverters where we have some form of inductor in there to basically, again, smooth that, that DC current and voltage within there. So you can see on the left-hand side that we have a very simple sort of RC circuit. The resistor in there is mainly for sort of what's classed as a charging resistor to charge that circuit up, during the startup period. And you can see on the left-hand side there, we've got that rectified signal coming in from the left. And then as a result of that going through the DC link, we now have a much more smoother sort of DC voltage, at least, where you can see initially we have that sort of charging time because of the capacitors to get it charged to the DC voltage point, and then from there we have a very sort of constant voltage. Now on the right hand side you can see there's a little bit of ripple that I've applied onto there. A lot of drives in in this day and age that there'll be very little ripple on there, but I've just sort of exaggerated on that a little bit just to give you a bit of a flavour of what it typically would look like. But that ripple in variable speed drives today, it can be anywhere. It's very small. It can be within 1 volt, if not less, at least. But it's just to give you a bit of an idea that there'll be some ripple in there at least. But yeah, it's not as bad as that is, at least anyway. So yeah, one thing to make warning of as well is that because of when we apply an AC voltage, we're actually going to have a higher sort of DC bus voltage on the output. So we typically say, this is more from a safety aspect, that when you power a drive down, is to wait at least sort of 5 minutes before you carry out any work on there, and that's just mainly to give the capacitors enough time to discharge any excess voltage out of there. Back into the ground system, at least anyway, because it's quite easily that you could power down the drive, start working on it, and then you make contact with the capacitors, and then there's a short there to work potentially, or to somewhere on the system at least, where it can cause some damage not to people but on the drive itself as well. So yeah. So as I said before, on the right hand side there's a typical sort of circuit diagram of what the DC link would consist of, and you can see there where the capacitors are, and then typically there's the charging resistor in there as well, which it's normally called a pre-charge circuit, where once the capacitors are fully charged, you then have some form of bypass switch in there that will then bypass the resistor and then go straight to the capacitors. So, as we were saying before, to actually vary the speed and the frequency and the voltage, to the motor, so we have to convert the that AC signal coming into that drive to a DC, which we've done here. But to have full control of that speed and the voltage and the frequency, we now have to convert that by going back from DC to AC, and that's still done by a set of 6 what we call Igbts. And the best way to think of these Igbts as switches, where what will happen is that the drive itself will have some form of control microelectronics in there, with some sort of microchip controller, where depending on what you set the speed or frequency to, depending on what control method you're using, that will essentially control the timing of when these Igbts, or I should say switches, will open and close. So we have this sort of DC link voltage that's going into the Igbts, and depending on the sequence of those switches, they will switch on and off to produce and basically it's still classed as a DC signal coming on the output, and you can see the little red pulses on there. And that's what the drive generates. It's a set of pulses which vary in width, and it's also known as sort of pulse width modulation, where we're varying the pulses by frequency and and amplitude as well to vary the voltage and the frequency to give us that required speed change in the motor. Now, although that's being sent out from the output of the drive side, the motor in reality doesn't exactly see that, whatsoever. And all the motor will see is effectively the algebraic sum of that, which is this sort of black kind of sawtooth sine wave signal in there, because at the end of the day, it's not a perfect sine wave signal that's generated on there. It's perfect enough that the motor will acknowledge that and will operate. But to be honest, I've just, again, like with the DC link, I've kind of over exaggerated, because in reality, you would not get something as rough as that. It'd probably be something a lot smoother, but you'll see some little some minor jagged edges at least anyway. And again, as a result of all this, it all varies on what's on the output of there, but also what the overall length of those cables are going to be as well. And it's typically the longer the length of the cables, the motor cables per se, we then have to put extra measures in there to make sure that we get a more pure sine wave signal, so that we don't, cause any significant damage to the motor insulation and the motor itself to break down. In terms of why do we need drives, and we're comparing this against sort of direct online starting AC motors, here's pretty much a list of sort of the common problems when starting and stopping motors using direct online methods, and how a drive can solve all of these problems. Now, I'll give you just sort of a moment or two to have a read through those at least, but just to pick some of the key highlight some of the key ones at least, is that the first one straight away is that with direct online motors, there is always, as soon as you start it, there'll be a massive high inrush current that's being applied to that motor, and that can be typically in the region of about 6 to 8 times what the motor's sort of full load current or motor's nominal current is, too. And as a result of that, you're going to have a very high starting torque. And because of that high starting torque, it's going to do a lot of hammering onto that motor, where if you've got like bearings, couplings or gearboxes connected to that, it's going to produce quite a high sort of wear and tear on there, to a point where, those parts of the system will start to break down in shorter time, not in a short space of time, but over a certain period of time it will do so. The drive, however, is able to fully control the current, so that during startup, it doesn't require more than what the load requires, and that typically, as a rule of thumb, is that it will normally require what is the motor's nominal current or the full load current, unless it's a sort of a heavy duty application where you might need a little bit of an overload, where typically as a maximum, probably looking at about 1.5 times the motor's full load current. With a drive, it's very rarely that you'll go much higher. You won't, if anything, you won't go higher than that at all as well. The other key thing as well with direct online, as we mentioned before, is that they only ever operate at one speed, whereas with a drive we can actually vary that speed to a point where, depending on the type of load that's being applied onto there, we can actually produce some form of energy saving as well. And that can be as much as 80%, and it all depends on what the load requirements are and what the load type is as well. And the drive has a very clever way of being able to report and calculate those savings as well, depending on what you've got set up within there as well. Good things as well is that you're able to protect against any pressure surges or water hammering in pumping systems, because as a result of that high starting current and torque, you're going to get a lot of water hammering in pumping systems, where the drive actually relieves that, so that you're not getting that constant pressure surge or water hammering, so to say, at least anyway. So why use a VSD in at all, really? From an energy and control perspective, Some of the key things about using a VSD over sort of the more traditional starting motor or motor starting methods, such as direct online, star delta starting, or soft starter starting, is that we've seen that you can actually reduce the overall speed on a drive to a point where you can actually accrue some form of energy saving depending on that load and application. And we've also seen as well that you can start at nominal current and torque when required. And that's very key when you're looking at a big motor in a weak network. If we compare this from a soft starter per se, if you're trying to start a big motor in a very weak network where there's not enough power to get it started, a soft starter typically needs as a minimum in the region of about 2.5 times the starting current to get it up and running. Which sometimes might not be enough, within that weak network. Whereas with a drive, as we've seen previously, we'll only need about either the motor's nominal or around at the maximum 1.5 times the sort of motor current, to get it started. Drives have a much more precise start or stop ramp time when required. So the drive itself actually controls the motor to a point where it will stop very accurately within a number of seconds. Whereas with a direct online or star delta starting, if you stop that motor, you basically stop it to a point where it just effectively coasts to a stop because of the inertia that still could be present in that motor itself. And a drive itself can coast to a stop as normal, but there are options in there to put a more controlled stop or start in there, so you can start within a certain period of time, but also stop within a certain period of time as well. Brake time and capacity. Unlike some of the other methods, the drives have the ability to do some form of braking in the form of, and there's two forms of this: mechanical braking, which is basically a mechanical brake that's fitted onto the motor itself. But what we're looking at here is more electrical braking, where certain applications, if we take a conveyor for example, where they have to stop them very quickly within a quick period of time, to a point where the motor is going to act as a generator and start dumping that voltage back onto the drive itself, or start to dump it, upstream of itself at least anyway. The drives themselves, with one or two options, have the capability of being able to convert that electricity back into heat and dump it on basically a DC, sort of common DC braking system. We do have other options as opposed to dumping it onto a DC braking system. We can actually use a regen drive that can actually, depend on how often it's going to be generating, instead of dumping it onto a DC brake, we can actually regenerate that voltage back onto the mains and ultimately put an overall sort of energy saving on there as well. But a good thing as well with a variable speed drive is that very easily you can reverse that motor in full or partial speed. Now, I understand with sort of direct online, star delta, and even with soft starters, there are options in there to, if you want to put something into reverse, you can do, but you could only ever do that in full speed. But you'd have to have some form of additional contactor to basically reverse those, reverse a pair of those phases to get that reverse speed. Whereas with a drive itself, you don't need to do any physical changes whatsoever. You just effectively put 3 cables in, or 3 wires in, 3 wires out to the motor, and then you can, once it's commissioned, run in forward but also in reverse as well at a particular speed. From an energy perspective, typically, as an overview, 60% of industrial electrical energy is consumed by motors. And that's just in the industrial sort of industry itself, where it's nearly all of those, in the region of about 95% of all motors, are oversized. And the reason behind that is more typically from a safety perspective, to a point where if the designer is designing a pump or a fan, although depending on what torque or powers that needs to be absorbed to get that fan or pump running, they will normally sometimes depending on that, they will sometimes oversize the motor to ensure that there's enough torque or enough torque being applied to that system. Or it could be that from a sizing perspective that they've got an absorbed power of say 100 kilowatts, but they haven't got 100 kilowatt motors, so they may go to the next sort of standardized or typical motor power, at least, where typically in this case it'd be 110 kilowatts for a standard induction motor, but if we're looking hypothetically, it could be a lot larger than that, where depending on the type that they're using, at least anyway. So looking at the various load types, when type systems are oversized, there are typically two basic load types on drives when sorry, rephrase that, sorry, that obviously drives themselves save energy by varying the speed of the driven load. So we'll see in the next couple of slides, by reducing the speed we can save energy, but there are, in parallel to that, two basic types of load. There are variable torque loads, and the other one's constant torque loads. They're where the majority of applications sort of fall under. So variable torque loads are effectively loads where the power of those vary with the cube of the speed. And as a typical example, we've got things such as centrifugal pumps and fans, cooling tower fans, and to a certain degree, some fairly basic compressors as well are classed as variable torques. Whereas with a constant torque is a load where the power itself varies linearly with the speed itself. And as a typical example of a typical constant torque load, we've got things such as conveyors, extruders. Again, majority of sort of screw type air compressors, but the majority of compressors are constant torque. There's probably a small percentage where they are classed as variable torque, but you've also got things such as positive displacement or vacuum pumps, hydraulic power packs, and punch presses, where they're more typically classed as constant torque applications. So going back to the variable torque sort of load, the actual, as we've seen, is that the power is proportional to speed cubed, and this is a typical sort of overview of how that that variable torque varies in relation to speed and power. And you can see here that by depending on the application and if you've got enough demand, depending on the demand that's required, we could very easily reduce that speed to say 80%, so reducing it by 20%, and we can provide some form of energy or power saving up to the region of 50%. If we wanted to crudely, we could actually reduce the speed again by 50%, and have significant energy power savings within there as well. But this all depends again on the load itself, on what demand's required, because a lot of sort of pumps, I know pumps in particular require only they have like a minimum speed that they can only operate to, or a particular speed range that they can operate to, where too fast can damage the pump, but even too slow as well can over time damage the system in general. And this sort of power flow relationship is what's considered sort of the cube laws or the affinity laws, where if we where the power is the cube, a cube, or the speed cubed, and the flow is typically the speed squared, and the actual head is typically proportional to the speed itself, at least anyway. So the majorly variable torque loads yield the best savings because of that cube relationship between the speed and power. And we can see here that for a typical sort of variable torque application, we've put there, this is the actual power that's needed to produce the required flow for this pump. Now, if we looked at a DOL sort of direct online pump that's being throttled, to control that flow, we're probably going to get something along the lines of that, where as the flow increases, our power is going to increase up to a point where if we get near to sort of 100% flow, it'll start to sort of flatten off and become constant, where by utilising a VSD to achieve the required flow, we get something a lot more accurate to what power is actually needed. And as a result of that, because typically motors are oversized for various reasons, we can actually yield some form of energy saving as a result of that as well. So you can see there, that's typically that shaded region is where the number of, or the amount of power we've saved, and that can vary depending on a case by case basis really. All depends on the flow and demand required. So yeah, so it's the majority of times most pump and fan systems are oversized, so it can nearly always, so the speed can nearly always be reduced, to yield some form of energy power saving. So as I said previously, that flow or head is proportional to speed, and this is part of the cube laws, where torque is proportional to speed squared, and then power is proportional to speed cube. So if we take this example that in this sort of typical application where we've got power and torque, even if we just reduce the speed by 7%, so 3.5 hertz, if we're controlling the frequency, can yield anything up to sort of 20% in an energy saving. And the further we reduce that, the more energy that we can save within reason, at least anyway. If we look at a constant torque load, however, power is effectively proportional to speed. So as we can say, it's a linear pattern as opposed to being sort of slightly exponential with the variable, where regardless of where we vary the speed, we're also effectively going to get the equivalent proportional power to that. So at 100% speed, we're going to get 100% power. 75% speed, we're going to get 75% power. And 50% speed, we're going to get the same in terms of power, again 50% power. And it's from that we may, if you, by altering the speed, you may have some form of, you may have a slight small energy saving, but not as great as what you get on a variable torque. And constant torque loads in essence do not save as much on speed reduction, and where their savings come from is actually taking control of the system. And it's where, if we look at sort of air compressors and hydraulic power packs, whereby being able to control the pressure that's being fed through there, we can actually start to put some form of energy saving in there by means of using some form of PID control, where if we look at the air compressors, where most factories have these, to supply air for tools, etc. A lot of the time that these are ran sort of 24/7, but they're not always going to be on load constantly. So there's going to be various, if we look at, depending on shift patterns or the amount of work that's done during the day, depending if it's like a day shift or whatever the pattern is, it's always going to be running, but you're not going to be always on load all the time. So in terms of an air compressor, when an air system reaches pressure, they continue to run, and then what they do then is, by means of a valve, they then vent that out through a valve of any excess pressure. And it's very similar again to hydraulic power packs, is that they generate hydraulic fluid at pressure for operating machinery, and they are run constantly, but again not on load constantly 24/7 typically. And again, when the hydraulic fluid reaches that pressure, they continue to run, and then it's via a burst valve. They then vent that, it's then vented through there. Now, both of those systems can benefit greatly from PID, because what we can do, and I won't go into too much detail, is that we can look at the feedback of that pressure, and depending on what our set point is, we can start to vary, the speed of our drive and motor to meet that demand, basically. And once we're at a point where we've met that demand, we can then actually start to slow down the system to a point where we can come to a complete stop, and it'll only speed up back again if demand or pressure starts to drop to a certain point where we need more to keep the system running. So the last part is now looking at what do we need to consider when we're using a VSD. So this is looking at terms of size and any options that we need to consider, as part of the complete sort of drive system installation. From a dimensioning perspective, I won't go into too much detail, but these are sort of the typical things that you probably need to consider, to name but a few, when dimensioning a drive, for a system. So you need to look at things such as the, where the supply is coming from. Is it a private or industrial site where it's got its own dedicated transformer, or or is it a public network where the supply is shared with others, where as a result of that we need to consider Harmonics perspective, because a lot because drives or electronic equipment can they can produce harmonics to a certain degree, and we've got to take that into consideration. But as well as that, we've got to define the AMC compliance required as well. So again, depending on the supply that we're connecting to, we need to consider whether it's industrial or a public network. And if it is a public network, we need to increase the EMC compliance required within there as well. Other things we need to consider is the actual location of where the drive will be. Ideally, you'd like to keep it as close as possible to the motor, but if we take a submersible pump, for example, it's not always ideal that the drive will be close to the motor. It could be anywhere in the sort of hundreds of meters where the drive will be installed and where the actual motor will be where it's being driven. So we have to consider what the motor cable lengths as well, and any options that we need to consider to basically to fit onto there to ensure that we ensure that the motor is being prolonged for a very long time, really, from any failures. But also need to consider things as whether is the motor close coupled to the pump, or is it connected via a line or prop shaft, or is it connected to a set of belts as well. But we also need to look at whether this will be a brand new motor or whether it's an existing motor, and whether we need to basically consider again, if it's an existing or new motor. If it's an existing motor, we need to check if that motor is capable of being inverter driven, where a lot of motors in this day and age now, a majority of them now are inverter capable or can be driven by an inverter. But this is more some of the older variants of induction motors where the insulation class on them was not very high, and that putting the drive onto there would eventually break down that insulation and cause a fault on the motor itself, where we'd have to look at additional options to to mitigate that, at least anyway. So in terms of looking at harmonics and cable lengths, there are a couple of options to consider when using a VSD. From a harmonic perspective, there's the means of input AC chokes or DC chokes, where a lot of drives, typically these will come as standard, and they come as standard with ABB drives, at least anyway. It's normally with the smaller drive sizes will get a DC choke to help sort of reduce harmonics on the system. But on the larger size of drives, you'll have a choke on the AC side, or the input side at least anyway. And both of those again are used for harmonic mitigation, and in some cases they're used to protect the input bridge from heavily sort of notchy supplies. So things like generator supplies or a very weak supply will can protect, or an unstable supply can protect the input side at least. But there's, as a result of these, typically there is a voltage drop issue that we need to consider that normally is not very high. It's normally at a maximum typically in the range of about 2% on there. We tend to use sort of DC chokes on the smaller size drives because they're more usually a cost benefit, where it's much more cheaper to use a DC as opposed to an AC. The larger sizes, it's more beneficial, not from a cost perspective, but from a performance perspective, to go with an AC one as opposed to a DC one. On a lot of the older sort of drive technology, they used to have these things called a swing and choke. And what that did, it's very similar to sort of kind of like your passive filters for harmonics, is that the impedance on that would alter with the load, so that the system will optimize the impedance to get the best sort of harmonic performance. But in this day and age, you probably very rarely see that now, at least anyway, on new drive products. But from an output perspective, and this is more when you're looking at long motor cable lengths, is using output chokes or DU/DT filters. And if we refer back previously how the drive produces that sort of PWM signal, there are certain periods that those pulses can produce very high peaks at the startup, to a point where it can be anywhere sort of up to sort of 2 times what the motor nominal voltage is. And depending on the motor that you're using, will in certain circumstances will not like that, and over a period of time the insulation will eventually break down as a result of those high peaks. And that normally happens, or the increase in peaks typically happen because of the long sort of motor cable lengths. So they either can be very long, or if they've got a very high capacitance in there at least anyway. And what sort of output chokes and DU/DT filters do, they effectively help reduce the overall peak voltage, but also the rate of rise of volts with time, reducing those voltage spikes that are caused by long or highly capacitive motor cables. But one thing to note here, and it can be a lot of people can get very easily caught out upon, is that output chokes or the DT filters do not improve the EMC performance. So it can be very, don't get caught out on that. If it's an EMC issue, it could be more something to do with the cable inside, or you've not got an adequate sort of EMC filter fitted onto there at least anyway. Also, from a harmonics perspective, these are the typical sort of gist of idea, levels of what harmonics are produced on drives, contributing towards the system at least anyway. Where I've put a couple of examples on there to give you a flavour at least. But on the left-hand side, we've got the typical harmonics for what we class as a 6-pulse diode rectifier. So the best way to think of the pulse is the number of components, or the number of diodes on the input. So a 6-pulse drive or rectifier just means there's 6 diodes on the input. So if we had a typical 6-pulse drive with no sort of harmonic reduction on there, so no chokes or filtering, you're going to get typically a total harmonic distortion anywhere in the region of, from a current perspective, from 40 up to anywhere, up to 120%. And that will vary depending on the loads that are connected on the system. And this these percentages are just based on the drive itself, not this is not taken into consideration any other loads that will contribute to harmonics on the system. So this is just looking at the drive as a standalone system. If we sort of improve upon that and add an input reactor, which comes with a standard with the ABB drives, and that's typically I think it's a 3% sort of input reactor. You'll get a total harmonic distortion from a current in terms of current anywhere from sort of 32 to 48%. So I know with our drives with a standard sort of input choke on there, you're looking in the region of about, I'd say, 40% total harmonic content you would get at least anyway. But we can also improve upon that by having a 6-pulse drive and then applying an input passive filter on there, where we can significantly reduce the total harmonic distortion from anywhere to 6% and typically as a maximum to 12%. There are other methods to sort of reduce or mitigate harmonics on a system. We can go for multi-pulse or multi-phase systems, where instead of having a 6-diode pulse rectification, we can have either a 12 or 18 pulse, where we just basically have an extra bank of diodes on there, where they're connected to basically different sort of windings on the output transformer, where as a result of that sort of phase shift, we're able to cancel out certain harmonics on the orders at least anyway. So a 12-pulse drive, or rectifier I should say, will produce a typical harmonic distortion anywhere from about 8 to 12%, whereas if we have more on there, so anything greater than 18 pulse, we get a harmonic distortion of anywhere from sort of 4 to 8%. We also have the option for, as well, this is something that ABB offers, is in the form of our ultra low harmonic offering or regen offering, which is the active rectification option, or an active filter as well, depending on what you've got on there. Now, active filters themselves probably produce harmonics slightly above 3%, but typically dependent on the load and the system itself. A typical sort of ultra low harmonic active front end drive will produce total harmonic distortion in the region of anything less than or equal to 3%. From a EMC perspective, so what do you need to consider when using a VSD, when sort of EMC bearing currents in the actual driven load itself? Something to consider is basically things such as RFI filters. So they allow the drive to conform to the EMC directive, but also mostly prevents conducting emissions. But that the RFI filters control one side of that. It's normally typically the other components, such as the cable shield, and ensure that the radiated emissions are controlled at least anyway. Apologies, sound just went off again, so apologies. So going back to the filters, etc. So we've got the RFI filters in there, that a lot of those come as standard with our drives, but there are options to improve upon that or to remove it altogether. But another thing as well is having common mode filters on there, or what's also known as ferrite rings, where they're either mounted either on the DC component side of the drive or on the actual output side. And what that does, it magnetically connects all of the conductors, reducing any sort of common mode noise. So basically any noise that's going to earth, and as a result of that, protects sort of motor bearings on larger drive systems. Smaller drive systems very rarely tend to have this sort of common mode noise. It's more predominantly on larger drive systems. But another thing as well, and this can, when we're either feeding a transformer or we have a motor with a very poor, insulation, is a sine filter. And what that does is effectively converts the voltage pulses at the output of the drive into a much more true sine wave. And that's only from the voltage perspective, because the current waveform is already sinusoidal, at least anyway. But one thing to mention when we're using a sine filter is that at the sacrifice of using one, they have quite a substantial sort of volt drop on there as well, and that can be anywhere in the region of about 10 to 15% at least anyway. So you have to consider that at least anyway when you're using a sine filter on the system. In terms of bearing current, so high frequency common mode circuit noise, is that a drive system, is composed of the following, where we've got the supply, the drive or frequency converter, the cables, the motor and grounding, and all of those together form a high frequency common mode circuit, where the frequency converter itself is a source of common mode voltage, and basically the motor bearing itself can become a part of that common mode circuit either directly or indirectly by secondary effects. And it's not to say that this is a failure of the AC drive system, this common mode voltage. It's more of a feature loosely because it's a consequence of sort of two-level PWM's common mode voltage and current, and sort of the current machine designs that's, as a result of that, it's come into effect. As I said, it's sort of larger motor powers and drive powers where this occurs on, so typically anything sort of greater than 100 kilowatts, and the higher sort of DU/DT, so the higher voltage and time rate of the converter and higher sort of supply net voltage increase the circulating current peak values, but a very high converter switching frequency as well increases that circulating current RMS value as well. And with IGBT converters, if there's no counteraction, the time to bearing failure varies from a few weeks to a few years. It all varies on how the system's been installed and fitted. And in terms of counteractions, the best way to sort of mitigate this is to ensure you have the correct cable and grounding, but also have any additional sort of common mode impedance on there via the means of a common mode choke, or either single phase DU/DT filters or reactors, or having a common mode filter on there. But also what helps with this is having insulated bearings on the non-drive end of the motor. So this can be part of an insulated or hybrid bearing, or an insulated end shield, which a lot of motors in this day and age come with. As soon as they're aware that a drive's being connected, they'll make sure an insulated bearing is there anyway. And I think with a lot of manufacturers, they're there as standard anyway. But yeah, the majority of damage on larger motors, the majority of this is caused by circulating currents, and the shaft grounding itself on the motor, or the shaft grounding currents, is usually related to improper, basically miscabling or grounding arrangements. So using the incorrect cable type or cable shielding, but also how the motor is being driven in that machinery installation as well. But on top of that, we can get some form of capacitive discharge currents, which may be a problem under very specific conditions on small LV motors, but very rarely that happens, at least anyway. Other things to consider, when using a VSD in terms of operating conditions, we have to consider sort of the ambient temperature that the drives are being installed in. So typically a drive can operate up to 40 degrees Celsius. Anything above that, up to sort of 50 degrees Celsius, you'll need to apply some form of derate. And in certain circumstances, if we want to improve the overall motor control, we may need to increase the switching frequency, which As a result of that, the higher the switching frequency, the more power is being used to switch those semiconductors on and off, so there's more heat being generated. And as a consequence of that, we have to sort of derate the output current on the drive to accommodate for that as well. From an altitude perspective, again, typically drives can operate anywhere up to sort of 1,000 meters above sea level. Anything above there, so anything above 1,000 meters up to 4,000 meters, we then have to apply a derate onto there as well. But we need to consider the environment it's being installed in, whether it's a very harsh environment where it could be exposed to dust and or humidity, or even sort of splashing or spraying water, where we need to consider, to go for a higher IP variant drive system, but also ensure we've got the proper filtering and prevention of hot air circulation inside the cabinet itself. When we're mounting the drive within a cabinet, we have to ensure that there's adequate filtering in there to circulate that hot air that's being generated. In terms of some special cases, here's a couple of things that we need to consider at least. So in terms of when we're looking at old motors and retrofits, normally as a rule of thumb, a tip for adequate insulation on a motor, for it to be inverter capable, we typically look at something along the lines of Class F insulation. Anything less than that, it's probably almost guaranteed that that motor is not sort of inverter driven or inverter capable, at least anyway. But also on larger powers, we may need to have some form of DUDT filter on there as well. And the same can be applied as well, say borehole and submersible pumps as well. We need to consider the motor insulation, but also whether we need a DUDT filter. And sometimes these come as standard with the pumps. They may have some incompatible cables where they're non-screened, and as a result of that, can often cause EMC issues in the field, but can also cause EMC to ancillary equipment as well, where this can be not to, but also including measuring equipment on there. In terms of measuring motors and drives, should never really measure the motor when the drive's connected, as that will damage the drive components. But drives may trip on overcurrent to signal a winding failure. And we always say that it's always best to trust the drives, even if when measuring the motor it says it's okay. There's a good chance it's a good early indication that the motor could be on its way out, at least anyway. And to sort of summarise on that, here's probably a quick summary or a checklist of possible items that you need to consider when using a VSD for a particular application. So looking at the actual physical space itself, and consider how it will be installed, but also consider the supply it's being connected to and the harmonic effects of that. All the way to consider as well if there are any control cables or feedback signals that can be reused, and ensuring that if it's a new installation, that those control cables have adequate spacing from them to the actual power supply cables that are being used on there. And from that comes to the end of this technical webinar. So I'd like to say thank you very much to you all for attending this session.